special webinar, we are very happy to present a guest speaker, Jaroslav Navratil. I'm also very happy that so many of you registered and listened to today's webinar. Jara will speak about pre-stressed concrete design in RFEM using the upcoming completely revised RF-TENDON module, which will be available with RFEM 5.06 early next year. Jaroslav Navratil is a technical director of IDEA RS Limited, which develops structural engineering software solutions. He and his co-workers developed the RF-TENDON presented today. He also works as an associate professor at the VSB Technical University of Ostrava, where he gives lectures on pre-stressed concrete. He's a chartered engineer in statics and dynamics of structures and also a forensic expert in civil engineering. He's a recognized expert in the field of concrete and pre-stressed concrete structures, and his specialization is the development of methods for the design and analysis of structures. He published many technical papers and research reports, and I also want to highlight his textbook, Pre-Stressed Concrete Structures. The two colleagues on Dlubal's side that are responsible for the RFEM RF-TENDON module are Alexander Meyerhofer and Adrian Langhammer. Alexander is the main developer of the concrete modules that are available for RFEM and R-Stab. He takes also care of testing and product descriptions. Adrian supports you as users of concrete modules and the RF-TENDON module. He takes also care of the testing process at Dlubal. Today, both are answering your questions throughout the webinar. So you see all together that we organized a team of experts today, and I really hope that you will enjoy the webinar and that you will find it interesting. So now, just a quick word to the GoToWebinar control panel. So as you see, you should all see the screen on the right-hand side of your screen, and you can use the orange button to show and hide the control panel. And the most important bit is the chat option for you, where you can ask your questions, and Alexander and Adrian will answer all your questions throughout the webinar. And just in case there are too many questions coming in, you definitely get an answer, but it might be via email after the webinar. Some important questions, we might also summarize them at the end, and Yara might be able to discuss them at the end of the webinar if there's some time left. So that is all from my side. Now it is time that I hand over to Jaroslav Navratil, our guest speaker. Enjoy the webinar.
Thank you, Berlin. Hello, everybody. I would like to give you an overview of the features of our modules for tendon design, of pre-stressing design in RFEM. I will start with a short introduction to show the range of the application, and then we will switch into live presentation of how we can design post-tension slab in residential house. We will start with the modeling in RFEM. I will explain the principles of so-called result beams and the system rip and slab. And then I will switch into external module to show the tendon geometry, properties, losses, the effects of pre-stressing, and also some reinforcement design. And then I would like to indicate some practical examples which you will see in our future webinars or in our seminar in January next year. I also will indicate some topics for the theory which is used, which I will explain in detail during the seminar. These external modules, RF-TENDON and RF-TENDON design, are linked to RFEM by a COM interface. So they share a common data model, and it works, or these two modules work with the data from RFEM, and they give all the data regarding the tendons and tendon loads back to RFEM. These external modules use the power of the finite element engine of RFEM. About the range of application, of course, we can analyze both pre- and post-tangent structures, both 1D and 2D elements in either civil and industrial buildings or bridges. I will show, as I explained, post-tangent flat slab, but you can also use it for transfer beams, pre-stressed frames, or precast girders. As concerning the bridges, the use is, I would say, limited to cast-in-place bridges due to the possibilities of the analysis, or the prefabricated pre- or post-tangent girders. Now we should go to the first example, which is this post-tangent flat slab. You can see the picture of the model in RFEM, and also the picture of the model exported to external module with the continuous beam highlighted with the effective slabs in it. When I was thinking of what kind of example I would show, I was inspired by this residential house. You can see the visualization of the house, which was built some years ago in the town of Zlín in my country. This is a family house, but quite big one. The length of the house is about 50 meters, and the width is more than 25 meters. And I was involved in the analysis and design of this post-tangent slab, which was part of the floor of the roof of this house. You can see now the tendons designed in the slab, and we can also see final structure which was cast. It is quite a long span with the cantilever of more than 4.5 meters, and especially because of this cantilever we needed to use the pre-stressing in this family house. I will start my live presentation in RFEM. We will show what is necessary to start pre-stressing analysis in RFEM. So first of all, you have to define load case type pre-stressing and some load combinations, and also result beams and ribs and slabs. I will switch into RFEM, and we see that if I go to load cases, then I defined pre-stressing load case here, to which we store all the not only equivalent loads but also the results caused by the tendons, caused by the pre-stressing. Another load cases which I did in this example was selvate, snow, and the roof. In pre-stressed concrete, you should realize that your unit weight of concrete should be a little bit higher than 25 kilonewtons per cubic meter. Either you really calculate it based on the amount of reinforcement, or you simply use 25.5 or up to 26. So that's what I adapted to. Then we can see the combinations. I defined several combinations. We can, of course, define more of them to have the analysis more thorough, but this is necessary amount which I did. All types ULS and SLS characteristic, frequent and quasi-permanent, are used for the design. And you can see that first set of combinations is contain only solvate and pre-stressing. That's because we want to analyze the moment when the structure is pre-stressed before any other load is applied. Then I have a different set of combinations with solvate, pre-stressing, snow load, and the roof. So that was it. And last, which I want to show, is this model. You can see that we have I have defined some result beams, and the result beam, if I select one, is the member which is, I would say, dummy member or fictive member defined in the slab. If I open this dialog, we can define the area from which RFEM integrates internal forces from the slab into this, I would say, fictive beam. So you define the depth of the cross-section plus minus and also the width. You can also define different cross-section for the analysis and the design. As you can see here, we have these result beams here of the width ½ meter, and here we have 1 meter. That's because the cantilever here is much longer, and that's why we needed more tendons. If I switch into wireframe model, you can see this green lines, which are the tendons, and you can also see that the tendons are here distributed per ½ meter, and here the distance of the tendons is higher. Last one which I want to show is this beam and slab system. You can see here that I have a rib which is linked to the slab, and the RFEM can integrate internal forces from defined width of the slab together with the rib, and we can get the T-section, which I will show, T-section, which then is used in the analysis and in the design. Sorry. So next, what I want to show is the tendon, RF-TENDON, and the functionality of RF-TENDON, like tendon geometry, pre-stressing losses, and effects of pre-stressing. All the data from the model is uploaded to the external module, and we will see this shortly. After this RF-TENDON, I will show RF-TENDON design, and we have also the possibility to use all other functionality of RF-TENDON, of RFEM, like the nonlinear analysis of the slabs and so on. We have it already here. So this external module starts with the screen, in which you can see schematically how we apply load cases in individual construction stages. So first construction stage is the cell weight. You might have remembered that it was LC1 and LC2, and also the pre-stressing. And then at 120 days, we apply the additional dead load, like the weight of the floor. And in the definition here, you can, of course, add any combination which contains those two load cases plus possibly some live loads. The other combinations are the combinations 5, 6, 7, 8, which contained also the dead load caused by the roof. Then we can define the design members, and I already defined the member. I can show this 3D view, and you can see that I defined this beam and slab system with no slab above the supports and with effective slab width at midspan. We can also go to any other result beam, for example this one, which we have defined in RFEM. You can pick up the members. You can see, for example, this rib is composed of many members. So if you edit, and you can select the members from RFEM. In case that you have a curved beam, then we can uncoil it so that you can comfortably work in 2D environment and to analyze 3D tendon. In case of pre-tangent beams, you define in here in this dialog the parameters of stressing bed. Then we go to tendon layout, and we can see now X, Y, and XZ, sorry, XY and XZ projections. And if I want to make the beam in the real scale, then it looks like this. This is the plan, and this is the longitudinal section. If I switch off the plan because I am not interested in that, that will be the straight tendon, and then I can scale it in vertical direction so that I can work with the geometry of the tendon comfortably and with no problem. At the beginning, I define the material, number of strands, and also other properties like from which side we stress the tendon, material of the duct, and other things. But I can also, if I switch off this, maybe I do not switch off it, I go this one, I select one point of the tendon, then I can switch into geometry XZ, and if I really switch the drawing here, then I can get a nice explanation of the parameters, how this point of the tendon is defined. The distance is 43 millimeters based on the concrete cover. From the formwork, you can use the tendons, or this type of tendon which I use, this type of geometry, is composed of two segments. One is, both are closing segments because there are only two. And first is parabolic and straight with on the left hand side, and the last one is this one, straight on the right hand side. Except of these types, you can also, you see that we have either segments, segmental tendons, or we can also define polygonal tendons. Sometimes, especially abroad in English-speaking countries, they use for slabs only simplified geometry. Or we can import the tendons from text file, from table, or from template. If you make it once, then you can use it again, or from the XF file. There are also some possibilities of export. Last thing which I wanted to show here is this drawing of the tendon along the length. Maybe I can switch on the labels, and then you can see that I can produce, by defining these levels from the bottom of the beam, especially I would say from the formwork, I can define the distance of the spacer which should be placed, or to which the spacer should be placed with specific depth. For example, the spacer which is 300 millimeters will be spaced here at 9.18 meters. So the program calculates it for you. That's it. By composing 2D and 3D geometry together, we can get this 3D geometry, and what more, after we coil the beam, in case that it is curved, after we coil it back, then we add also this coding to the 3D geometry, and you can have such tendon. So you work in 2D environment and you have 3D tendon. And then we calculate the equivalent load, and we can display the load. Also, if I select the other rib, for example this one, then you can see that it is a little bit more complicated. You can play with it with the load weight. This is not a real scale. This is a real scale because above the support we have very small diameter. So you see that intensive load above the support in this small parabola. But if we want to see this equivalent load better, then you use this load weight. All these settings or possibilities on the ribbon are shown in the graphical tooltips. If I switch back to have it a little bit simpler to this beam, then I can show that you can see not only distributed loads but also point loads, and this is calculated from the deviations of the tendon along the length of the tendon. But then after we calculate this, we distribute it into distributed loads. You can also influence the precision by setting, for example, 1 degree here, and you can get more the forces. Actually, the smaller the angle is, the more precise equivalent load you calculate. But on the other hand, if it's too small, then it makes the calculation longer, of course. I can keep 1 degree, and we can get quite nice equivalent load. In some cases, for example, in 1D elements, you can also use the functionality of load balancing for the design of tendon force. As we have now the slab, then there is no direct load. I mean load per meter. We have load per meter square only, so the functionality cannot be shown in here. But the principle is that you balance the external load, selected external load, for example cell weight, or you can make also the combination of cell weight and additional dead load, and you balance it by the equivalent load caused by the pre-stressing. And the authors like T.Y. Lin or some professors in Swiss professors advise that you should balance approximately 100%, and if you design the Eurocode, then probably a little bit more percentage of these dead loads. After we have this defined, we can go to short-term losses. You can see these losses, also the checks of the tendon according to Eurocode and German annex. You can also have the summary of these tendon, in which you can read and display all the necessary information like minimum radius, the area of tendon, sum of lengths of straight and curved parts, cumulative angular angle along the length, and all these useful parameters. Design member results can be shown if we calculate RFEM, but before I do it, I want to explain. This is again the picture of construction stages, which actually can be used if you have different age of the beam in your complex 3D structure. And here we have the reinforcement zones. I have defined the reinforcement, of course. You can see the tendon here. Maybe I didn't show here in tendon geometry. Sorry about that. In tendon geometry, I probably should show this cross section. You can see how the tendon goes in by selecting the position of the tendon. Also, if I select the first rip and slab and I go like this, you can see the change of the cross section above the support. So we can check it. You can check it also in 3D. There are more possibilities which I'm not able to show you here, and possibly we will have more time during our seminars in Munich and Vienna. Now I go back to the reinforcement. I switch into more simple result beam. And we define, of course, we can add any number of zones. I believe that these can be sufficient for this case. And we can define the check positions. And in these positions, we then check the cross sections. So I selected the positions above the supports and at midspan. Now I press the button calculate FEM. In fact, the external module uses RFEM finite element engine, and we will get the results of all the load cases as combinations soon. It's not a small structure, but it takes reasonable time, so we will see it in a minute. And in the meantime, I will see if I forgot something. So we went through the segments of tendon geometry. We explained all the possibilities of polygonal, and now it is finished. I could hear it, but I finished this one. Export and import, pre-stressing losses, effect of pre-stressing, and all of these. Now we go to tendon design. We design the cross sections. In these pre-selected sections, we can go to RF-TENDON design, and all the data is prepared from the construction stages, from pre-stressing, and we find the cross-section in selected sections, and then the data is generated. Now we have 4 sections. This is above the support. This is at midspan. Again, above the support, you can see it in info window, and this is I think it was at the end of parabola. I can calculate all these sections, and as I already designed it, you see that it is satisfactory, 99% above the support. Let's see some results. Here we have individual construction stages. Stage at the pre-stressing, then when additional dead load is applied, and at 100 years. I will skip these data which in fact were filled in. You see, for example, let's say these construction stages were uploaded from the module. You can see how it changes, but we cannot change it as it was imported from RF-TENDON. But it is for your information. Also action stages, internal forces, there are all the losses and forces shown, and here you would define the reinforcement. There are quite nice possibilities of the definition of the reinforcement, and you can see the reinforcement, how it goes. But let me to explain these checks, concrete checks. And we have first we have capacity, in which we show the capacity against flexure and normal force in interaction diagram. Of course, you can see many possibilities on the ribbon. Shear analysis. Here it is interesting, and I wanted to show you that if we are at midspan, then the longitudinal shear is even bigger than a vertical one. You can see the direction of the shear force, and also the effective width of the slab. So we need both stirrups in both directions. If we select the section above the support, then you see that this direction of the shear force is vertical, and this one at the end it's even bigger. This is almost completely horizontal because of the shear leg. If we apply a high normal force of pre-stressing, then of course just behind the anchor we should not use the sectional analysis. This is anchorage zone, but I don't think I made it immediately after the anchor, and still RFEM integrates quite significant forces, but we can design them with no problem. So let's go back to the midspan. Oh, maybe I should have shown this torsion above the support, but doesn't matter. We have also the possibility to analyze the interaction of all internal forces, which I will explain later, especially during the webinar. Stress limitation, both concrete, I would say not both, but concrete pre-stressing reinforcement and non-pre-stressed reinforcement, crack width. Then some advanced, we have the possibility to check the detailing, but I switched it off here in settings. You can switch it. Oh, this is not switched now, but sometimes you have to switch it off because you do not provide a real reinforcing cage. And the response or stiffnesses response I can show here, and you can use this response to show all these stages. So that was at 28 days. You can see that there is quite significant pre-stressing at bottom fibers. Then at 120 days we have some losses already, and also higher load. So this is smaller, and at 100 years it is even bigger difference. When we are happy with the design, then we can go back to RF-TENDON, and we can switch into, for example, this rib, which was more complicated with complicated section, and again you define the sections which you really want to be analyzed and to be checked according to code, and the program again generates the data. In this case, I found a small problem with I can calculate all with the stress limitation. You will see in a second. So now we have here progress bar, and it shows you it's already done. What is what calculation is being performed, and here we have 102. 102. So how to check it? This is a section at 15 meters. You see it selected here, and the check which is not satisfactory, only by 2%, 2.6, is stress limitation. Then we go to checks, and you select stress limitation, and we see this is fiber in which the ratio of stress and stress limit is critical, so is extreme. We can also make this bigger. There is 13.9 megapascals, and it should be 13.5. The program tells you exactly what is happening in the cross section, and then you can sometimes, if it's straightforward, it gives you some non-conformity. For example, check of cross-section is not satisfactory, calculated compressive strength under quasi-permanent combination is higher than stress limit, and so on, so on. You can either increase this K2 factor in case, for example, that it happens during the pre-stressing in the fibers where you have the pre-stressed tendons. Then due to the fact that you measure all the forces in the tendon, you can afford to decrease R sub and R inf factors. But in this case, it is at the end, you can see that it is phased at 100 years. And in this case, either we say, okay, 2% is not that big problem, or we would have to increase the depth of the cross-section, or we can also increase the concrete grade. The other possibility would be if we go to reinforced to design and reinforcement, then I can select I can select zoom all. I can select this layer, and instead of diameter 12, I can try to use diameter 14, and I calculate current extreme, and I see that it is only 0.9%, so we can play with it. Maybe 16, diameter 16 would be okay, and it seems it would. So if we go back to sections and we calculate all, because all the data of that reinforced cross-section was deleted, then we see that the RIP in this case is satisfactory. Maybe we can go through all these navigator items, but I would prefer to finish the example, and we can concentrate on that in some other webinar or seminars. Of course, we can generate reports both in RF-TENDON design and RF-TENDON, but I think as the example it was enough, and we can go further. So I explained the design or I would say sectional assessment or sectional check in result beams and RIPs, but you might object that this is a 2D member, this is a slab. Then, of course, once you have designed these 1D fictive members, then you get some non-pre-stressed reinforcement as an additional reinforcement which has to be put into the slab. And you can also use the functionality of this external module, which puts the results, or I would say the equivalent loads, back into RFEM as an upward loads. And now you have one load case, like for example self-weight, which acts downwards, and of course pre-stressing acts upwards, and you can calculate, you can perform the analysis of 2D members, I mean 3D structure with the slabs, and you can also perform 2D design directly in RFEM. And after you have this potential additional reinforcement, additional to the one which we found in result beams, then you can also perform this non-linear analysis of 2D structures, to 2D slabs. We definitely will show it during the seminars. Now, as I would say a teaser a little bit, I would show other examples of pre-stressed concrete which we input in RFEM and which we analyzed in RFEM. This is a post-tangent slab bridge which we took from Prague University, Czech Technical University. It was published by one professor as an example of the calculation, but we used different model. You see here this exact shape of the cross-section, and if we simplify it, then we define this result beam. Each result beam would contain one tendon, and then we can use RFEM to calculate really 3D distribution of stresses caused by the moving loads, and then via these result beams we can design each, I would say, strip of the slab separately. So of course in each of these result beams we defined such tendons. I defined it exactly according to that textbook, and then we can get the results in RFEM back. This is the effect of pre-stressing and the upward deflection, and this view from the bottom of the bridge. Another example which we made, actually Adrian Langhammer input, is a double T post-tangent bridge. This was from a German report which I do not remember the name, but Adrian then can tell us. This double T post-tangent bridge was modeled in RFEM as two independent beams which were linked together by orthotropic slab. The slab had zero stiffness in longitudinal direction, because in longitudinal direction we had these beams, but it has some stiffness in transverse direction to make sure that those beams share the load applied only on one of them. So that was the model. Of course, we designed, you might have seen in the previous picture, the tendons. We designed the tendons and calculated losses and all other checks. You can see the checks in RF-TENDON design. First was a flexure check, and then shear, and also here the torsion check. I haven't mentioned that this equivalent thin wall section is calculated automatically. Last example which I would like to show is the pre-tangent tapered beam. You can see the longitudinal this longitudinal view, and also in RF-TENDON design the reinforced cross-section above the support and generated reinforced cross-section at the position at which we wanted to make the design. So in fact, if you use the templates of the reinforcement, then the reinforcement is adapted automatically along the length based on the depth of calculated depth of the cross section. After we showed all these examples, I would like again to indicate some topics which I would like to address during the seminars. So it is a kind of theoretical background. Definitely we will be speaking about the losses. This is a picture of longitudinal profile of the tendon and frictional and anchorage set losses. We will also discuss how the effects of pre-stressing are applied to the structure, that it comes from the deviation of the tendon, and this deviation is a source of radial forces, and then we can get this resultant force, and the resultant force is then applied in the form of equivalent load. You can see the picture of all loads, Fx, Fy, all the moments applied in a 3D structure it was curved structure. Of course, it is uncoiled here, so you can see complete set of loads. Then we should be talking about the background of sectional design. We see ultimate limit states and serviceability limit states, all the list of the checks. Anyway, you saw the possibilities in RF-TENDON design, and here you can see also German and Austrian flag. So we have national annexes of DIN code and norm. For the analysis of the sections loaded by bending moments and normal forces, we will discuss the methods, first decompression state method, but also initial state method, which we introduced in RF-TENDON design. We will touch also the shear analysis, the equilibrium conditions, and how from these equilibrium conditions the Eurocode formulas are derived. And what more, what is the role of lever arm caused by the flexure in the shear analysis? That's will be also a topic. And last but not least, we have a nice feature of interaction of all internal forces. You can see all internal forces here, and this is just the explanatory picture how you can do it to combine shear force and bending moment. So that was all from my side, and I would like to pass the presenter to Gerlinde. Thank you for your attention. I'm very happy to have you with us.
Many thanks, Yada, for the very interesting and informative presentation. So I myself found it very interesting. I hope you all enjoyed the webinar. Now we still have time for, sorry, I've just noticed that Yada mentioned the seminars. So the seminars will be held in January in Munich and Vienna, and you will be informed about this by the Dlubal newsletters, and you can also register online. As you see here on the slide, that's our Dlubal website. You can always register online, and if there are any questions, you can give us a call, write an email, so the usual ways to contact us. So there might be still a bit time left for some questions. We looked through the questions that came in, and I would like to highlight two of them. and that might be of general interest for all of you. So there's one question. Could you please summarize the new features of the new RF-TENDON and RF-TENDON design modules compared to the old versions? So just a very brief summary.
Okay, I can do it. In fact, we advanced a lot. That was quite a nice development, possibly the biggest contribution from our side were the national annexes of Austria and Germany. So we have it, and we have it done properly. I would say, I was sorry for saying so. I would say in German way. So hopefully you will like it. We also improved our reinforcement editor. Inside of the editor, you can use undo and redo function. You can define the zones. You saw part of the features before, so reinforcement zones. Of course, on the RFEM side, we improved it significantly due to these result beams and the system rip and slap, because this is something which was not there before, and it is very useful for the analysis of 2D structures. I would say you can use it also, I did mention that you can use it also for more complicated examples. If your tendon is curved in plan, then our result beam does not need to be straight, and we can analyze quite complicated shapes. As concerning the tendons, we introduce multi-editing of tendon properties, which I haven't shown, but we can show it during the seminars. We have also, I think I did mention tendon templates. I didn't show it, but once you use specific type of tendon and you want to have it saved, and you save it, and you for your next structures you can use it. As concerning, if I remember, the design of the sections, then we edit also fatigue checks. So I think that that's it. Maybe I forgot something, but anyway, you will see when you test it.
That's great. This was a nice summary. Thank you very much. And I found another interesting question. Is it possible to export and import the geometry of the tendons to or from a DXF file?
I can show.
Okay, great.
I will select this one. This is a little bit simpler, and I go to tendon layout, and you see you can draw current tendon, for example. You can set the labels, which you will see that there are radius, length of the parabola or part of the tendon, and cumulative angle. And I will switch this to here. So now you can prepare it. You can also change the grid. It is here. You can define either equidistant or non-equidistant levels. I do not want to go further. But after you are happy with the picture which you produced, then by pressing the right mouse button, sorry, my mouse is, you can go to DXF file. Okay, you export it as DXF file. So it is possible, and you have a nice draft drawing already. Okay, you can also draw all tendons. If you have more tendons in this, you can draw one tendon after the other, but in this result beam we have only one tendon, so we cannot show it. Okay?
Okay, great. This seems to be quite easy. Thank you very much. I think these were the most important questions, and now it's already an hour gone. So, Jada, could you please change back to the next slide? So I just want to finish up the webinar. I want to thank you all for your attention. And just to emphasize, you might know all about this. So there are more webinars upcoming next year. There are the seminars that we mentioned in January. You can usually watch our previous webinars. They are recorded, and you can just have a look to our website in the section webinars, and you can download the recorded videos or just watch them directly. And as you know from this webinar, you register online at www.dlubal.com. And now I just thank you for your attention. And it was nice to have you here. Many thanks.
Thank you very much. Bye-bye. I hope
Bye.
I'll see you in Munich or in Vienna.
That's great. Thank you.
Bye.
Bye.